Welcome to today's deep dive. You know, when you picture a medical diagnosis for yourself, there's usually this expectation of absolute precision.
Right, like engineering level precision.
Exactly. I mean, you break your arm, you go to the hospital, and the X-ray shows that stark, jagged white line. The doctor just points to the screen and says, well, there it is.
Yeah, it's a very binary way of looking at medicine. It's either broken or it's not.
Right. It's clean. And frankly, it gives you a very reassuring kind of certainty as a patient. But then you step away from the bones and into the world of gastrointestinal medicine.
Oh, yeah. That is a whole different ballgame.
It really is. Specifically, I mean, when doctors are looking for subtle, hidden, like precancerous cells inside your digestive tract, suddenly that crisp X-ray certainty is just gone.
It's completely gone. You're looking at a diagnostic landscape that is incredibly murky.
Yeah, because you're navigating through tissue that, to the naked eye, all looks roughly the same fleshy pink color, right? Even through a state-of-the-art camera.
Right, and it's the absolute definition of diagnostic muddy waters. Because the changes happening at the cellular level, the dangerous ones anyway, they can be virtually invisible.
Because they haven't actually caused a lump or a bump yet.
Exactly. They haven't caused any major structural changes. So to a gastroenterologist looking through an endoscope, a patch of healthy tissue and a patch of precancerous tissue can look completely identical.
Which brings us to today's deep dive. We are exploring a method that cuts right through that visual murkiness. And honestly, when I was reviewing the source material for this, I had to stop and reread it.
I had the same reaction, actually.
Right, because I wanted to make sure I wasn't misunderstanding it. Today's deep dive is built around this fascinating medical demonstration uploaded by a gastroenterologist named Gatakukala S. Raju.
Yeah, it's an incredible piece of medical footage.
It really is. It's titled, rather plainly, HCC 1475-21 acetic acid movie. But what this video actually shows is anything but plain.
Oh, it's mind-blowing.
It details how doctors are finding these invisible dangerous cells without using, a billion-dollar laser or some sci-fi AI tech. They're using acetic acid.
Which is literally just the chemical name for something sitting in your kitchen pantry right now.
Right.
Vinegar. Yeah.
It's just wild to me. The exact same stuff you whisk into a salad dressing or use to pickle cucumbers.
Yeah.
So that is our mission today.
It's a great mission.
We're going to unpack exactly how doctors use a basic household acid during gastrointestinal endoscopies to expose hidden, dangerous cells.
Yes.
Cells that the naked eye would otherwise completely miss.
It's a perfect example of elegant medicine.
Yeah. You look around a modern hospital suite and you see like million-dollar MRI machines and robotic surgical arms, and right in the middle of all that high-tech gear, they're using a splash of vinegar to save lives.
It's brilliant.
So, okay, let's unpack this. How exactly does an everyday pantry acid actually help find precancerous cells?
Well, the overarching theme here is that sometimes the most elegant medical solutions rely on simple, predictable chemical reactions.
Instead of just throwing complex machinery at the problem.
Exactly. In this deep dive, we are going to look at the precise mechanics of a phenomenon called acetowhitening.
Acetowhitening, okay.
Yeah, it's a brilliant example of using basic biology against itself to reveal what is hiding in plain sight.
Okay, but before we get into the actual chemical mechanics of why the tissue changes color, I feel like we need to understand the logistics here.
Sure, the delivery method.
Right, how are they getting this acid into the body? Because, I mean, if I drink straight vinegar, my throat burns.
Oh, absolutely.
So you're telling me doctors are taking acid and just pouring it down a patient's throat onto sensitive, potentially precancerous tissue. Doesn't that damage the very cells they are trying to save?
I mean, that is a completely natural concern, but the application is incredibly refined.
Okay, so they aren't just taking a bottle of Heinz and dumping it in.
No, definitely not. They don't just pour a bottle of acid into the digestive tract. It is a highly controlled, localized delivery system.
What does that look like?
Well, the doctors use a specific setup consisting of a spray catheter, which is a very long, very thin tube designed to deliver a really fine mist.
Oh, a mist. That makes more sense.
Right. And they attach a simple 20 cc syringe filled with the acetic acid to that catheter.
Wait, 20 cubic centimeters?
Right.
That is, what, barely over an ounce of liquid?
Yeah, exactly. So we were talking about a very small, very targeted amount.
Okay, so it's a tiny amount.
A tiny amount, but because it's delivered as a fine mist, it provides maximum surface coverage.
Got it.
And the geography of how they apply it is crucial, especially when we talk about a condition called Barrett's esophagus.
Okay, how do they do it?
The doctor feeds this spray catheter right through the endoscope. The camera tube they already have down the patient's throat.
Right. The camera's already in there.
Yep. They guide the catheter all the way down to the distal end of the esophagus.
So meaning the furthest point down, like the bottom.
Specifically, close to the gastroesophageal junction.
Okay.
That is the exact anatomical border where the esophagus meets the stomach.
Okay, so they go all the way down to that border, and then what?
Then they start spraying the acetic acid mist, but they do it in a very specific direction. They spray from the distal end, the bottom, and work their way up to the proximal side, moving backward.
Oh, I see. So if we think of the esophagus like a tunnel, they are driving the camera all the way down to the very end of the tunnel where it meets the stomach.
Exactly.
And then they're essentially painting their way backward. They're laying down this fine mist of acid on the walls of the tunnel as they reverse out.
That's a great way to visualize it.
Which makes sense, I guess. It's like you paint a floor and walk backwards so you don't step in your own wet paint. Right?
Yeah, or in this case, you pull the camera back so the lens doesn't smear the mist you just laid down.
Oh, right. You don't want vinegar all over your expensive camera lens.
Exactly. It ensures a perfectly even coat over the delicate tissue. They systematically paint the walls of the esophagus as they pull back.
Okay, so we've painted the tunnel. Now we need to talk about what actually happens when this acid makes contact with the internal lining of someone's throat.
This is where the magic happens.
What is the camera seeing as they paint their way backward? Because earlier you mentioned that term, aceto-whitening.
Right, aceto-whitening. This is the core concept from the source material.
Okay.
When the acetic acid makes contact with the Barrett's epithelium, which is the lining of the esophagus in these patients, a very specific chemical reaction occurs.
What kind of reaction?
Well, the healthy tissue, the tissue without any neoplastic or cancerous changes, reacts to the acid by turning completely white.
Wait, really? It just changes color from pink to white.
It blanches. Upon contact with the acid, the healthy lining turns an opaque white.
Okay, here's where it gets really interesting to me. Because normally we expect the quote-unquote bad stuff to turn a weird color to stand out,
Oh, like a dye.
Yeah, think about those plaque-revealing mouthwashes you use at the dentist.
Oh, right.
Your healthy teeth stay white, but the plaque turns bright purple. But here, the healthy tissue is the part that puts on a white disguise.
That's a really good way to put it.
It basically covers itself in white paint.
Yeah.
But why? I mean, what is the actual mechanism causing fleshy pink tissue to suddenly turn white just because it got misted with vinegar?
It comes down to how the acid interacts with the cellular structure of the tissue.
Okay.
To understand the mechanism, think about what happens when you crack a raw egg into a hot pan. Or, actually a better example, if you were to drop that raw egg white into a bowl of vinegar.
Oh, the clear gelatinous egg white suddenly turns opaque and white.
Precisely.
Because the proteins are reacting. The structure of the protein is literally changing.
Exactly right. The acid temporarily alters the structure of the proteins on the surface of the healthy esophageal cells.
Oh, whoa.
Yeah, they clump together slightly. And this structural change alters how light from the endoscope's camera reflects off the tissue. Instead of absorbing the light and looking pink and translucent, the altered proteins reflect the light back, making the tissue appear completely white to the camera. This is aceto-whitening.
That is fascinating. So the healthy cells undergo this temporary protein shift and turn white.
Yep.
But the real genius of this procedure has to be what happens to the unhealthy cells, right?
Oh, absolutely.
What happens if there is neoplastic, tissue-like dysplastic precancerous cells hidden within that lining? Do they just, not turn white at all?
Well, they do react, but this is where timing becomes everything.
Timing.
Yeah, the entire diagnostic process becomes a race against time. The doctor's watching the reaction happen in real time on the monitor.
Okay.
When the acid is applied, the healthy tissue turns white and stays white, only gradually fading back to pink over a longer period.
Right.
But the neoplastic tissue, the dangerous dysplastic cells, loses that aceto-whitening much, much faster.
Oh. So the healthy cells hold on to the white disguise, but the dangerous cells drop the disguise almost immediately.
Yes. The source notes that the dysplastic epithelium either doesn't take up the whitening as well in the first place, or it loosens and loses the aceto-whitening rapidly compared to the rest of the healthy columnar lining.
Right, columnar lining, like literal columns.
Yes, actually. The healthy cells in this specific area are structured neatly, stacked side by side like tiny columns.
Wow. Okay.
Because they are orderly and structurally sound, They hold on to that chemical reaction. They maintain the protein shift that keeps them looking white.
And the bad cells.
Neoplastic cells, on the other hand, are chaotic. I mean, cancer and precancer are basically defined by disorganized, rapid, messy cellular growth.
Right.
Because their internal structure is chaotic, they physically cannot maintain that protein reaction. The acid washes over them. They might briefly turn white, but they rapidly lose it.
Wow. So they paint the tunnel, everything turns white, and then suddenly, as they watch the screen, certain patches start reverting to pink while the rest of the tunnel stays white. The dangerous tissue is the part that loses its disguise too quickly because it's just too chaotic to hold on to the chemical reaction.
And if we connect this back to the bigger picture, you can see why this fundamentally changes a gastroenterologist's job.
I mean, yeah, it's night and day.
These rapidly fading, non-white areas suddenly act as a high-contrast map. We started by talking about those murky diagnostic waters, right?
Yeah, staring at a sea of pink tissue.
Exactly. Staring at pink tissue, knowing there might be microscopic precancerous cells somewhere in there, but having absolutely no target.
Because before this, what were they doing? Just like taking random biopsies.
Unfortunately, yes.
Just snipping little pieces of the esophagus and hoping they get lucky and catch the bad cells.
That's pretty much it. Standard protocol often involves taking random biopsies at regular intervals and just hoping you sample the dysplastic tissue.
That sounds so stressful.
It is, but by applying the acetic acid, the doctor forces the tissue to create a dynamic visual map.
That is so cool.
The loss of acetowhitening highlights the exact coordinates of the danger zones. It allows the doctor to target their biopsies directly to those rapidly fading areas.
So it turns a blind, hopeful search into a targeted precision strike.
Perfectly said.
It forces the invisible danger to basically announce itself.
Yes.
That makes total sense for a narrow space like the esophagus.
Yeah.
You paint the tunnel, you watch for the fading spots.
Right.
But the source material doesn't limit this technique just to the esophagus, right?
No, not at all.
If we zoom out and move further down the gastrointestinal tract, does this same chemical map perform just as well in massive open spaces like the stomach or on the flat surfaces of the colon?
The applications extend beautifully into those areas.
Really?
Yeah, the underlying principle, using acetic acid to expose chaotic neoplastic cell structures, it actually solves completely different geometric problems in the stomach and the colon.
How so?
Well, in the stomach, the acetic acid spray is used to define the extent of something called gastric intestinal metaplasia.
Gastric intestinal metaplasia. Okay, let's break that down for everyone.
Sure. It is a condition where the cells lining the stomach actually change to resemble the cells that line the intestines.
Oh, weird.
Yeah, it's an abnormal change, and it's often a precursor to cancer. And just like in the esophagus, it can be incredibly hard to see exactly where the healthy stomach tissue ends and this abnormal metaplasia begins.
Because the tissue looks too similar.
Exactly. But when the acid spray is applied, the differing cellular structures react differently, and it clearly defines the boundaries.
Ah, so in the stomach, it's really about drawing borders.
Yes, drawing a map.
It's taking a murky transition zone
Yeah.
and giving it a highly visible boundary line so the doctor knows exactly how far the abnormal tissue has spread.
Exactly. And that concept of drawing borders becomes even more critical when we move down into the colon.
Okay, what happens in the colon?
Gastroenterologists use this spray in the colon to identify what are known as sessile serrated polyps.
Okay, sessile serrated polyps. When I think of a colon polyp, I usually think of like a little mushroom-shaped bump growing on a stalk.
Sure, that's the classic image.
Something that physically protrudes and casts a shadow, which seems like it would be easy for a camera to spot, right?
Yeah.
What makes a sessile serrated polyp so difficult to find?
Well, what you are describing is a classic polyp, and those are generally easier to spot. But the word sessile essentially means flat.
Oh, flat.
Yes. These polyps lay almost perfectly flush against the wall of the colon. They don't cast a shadow.
Oh, man.
Furthermore, their color often matches the surrounding healthy colon tissue perfectly.
It's terrifying.
They are naturally camouflaged. Their boundaries are practically invisible to the naked eye.
So you are driving a camera through a very large, twisting cavern, looking for a perfectly flat anomaly that is the exact same color as the wall it's attached to.
It is an incredibly difficult visual challenge, and these specific flat polyps are highly dangerous if left unchecked.
I can imagine.
So, applying the acetic acid spray in the colon triggers that contrasting effect. The healthy colon wall reacts one way, the flat polyp reacts another, suddenly defining the hidden edges of the polyp so it can be identified and removed. But the source material details a highly specific, tense scenario regarding what happens after one of these flat polyps is removed.
Oh, right, because if the polyp is flat and camouflaged, how do you know you actually scraped all of it off?
Exactly.
It's not like chopping down a tree where you clearly see the stump left behind.
You've hit on the exact anxiety surgeon's face in that moment.
Yeah.
Let's say the doctor spots one of these flat, sessile serrated polyps and carefully removes it. Because the polyp was flat and its edges were so hard to see in the first place, the doctor is left staring at a fresh scar on the colon wall.
Okay.
The critical question is, did I get all of it? Is there any microscopic neoplastic tissue left lingering around the margins of that scar?
It's like cleaning up a spill on a carpet that's already a weird mottled color.
Yes.
You scrub the spot, you think you got the whole spill, but the carpet still looks damp and messy, so you aren't absolutely sure if you missed the outer edges.
That is a brilliant analogy. And in this medical scenario, leaving even a fraction of the spill behind has severe consequences for the patient.
Right. So what does the doctor do?
They use the acetic acid as a functional blacklight. They spray the vinegar directly onto the scar area.
And what happens? If there are lingering cancer cells around the rim of the scar, how does the acid reveal them under this functional blacklight?
It relies on that same cellular mechanism we discussed earlier.
The acetowhitening.
Right. The healthy tissue making up the normal colon wall will react uniformly to the acid. But if there is any serrated epithelium, any neoplastic tissue left behind on the margins of that scar, it will react differently.
It drops the disguise.
Exactly. It won't hold the acetowhitening. It will rapidly lose its color or stand out in stark contrast. The acid forces the leftover dangerous cells to visually separate themselves from the healthy scar tissue.
That is profound. I mean, the peace of mind that must give a surgeon in the room.
Oh, it's immense.
Instead of removing the tissue, closing up, and waiting weeks for a pathology lab to call and say, hey, the margins on that sample weren't clear, you left some behind, you need to go back in for another surgery, they can just spray a little vinegar on the scar in real time and know for absolutely certain if the perimeter is clear.
Yes. It provides real-time, high-definition tissue evaluation right there in the endoscopy suite.
That's amazing.
And at a fraction of the cost and complexity of advanced digital imaging methods, it answers the critical question instantly.
Which actually brings me back to an objection I raised earlier.
Okay, what's that?
Well, we are talking about spraying acid into the delicate lining of the esophagus, onto the walls of the stomach, and directly onto open scars in the colon.
Right.
The mechanism is brilliant, but surely this level of chemical manipulation comes with some heavy collateral damage to the patient. What are the actual side effects of doing this?
You know, the safety profile is actually one of the most remarkable parts of this entire procedure.
Right.
The source material addresses this explicitly. Despite the fact that it is an acid, the side effects are remarkably minor.
Minor. Just minor. Because I would expect at least some burning or localized tissue damage.
The clinical reality is very different. Aside from some temporary irritation resulting from the use of the dye specifically, the source notes a patient might experience mild esophagitis or gastritis.
Which is what exactly?
It's simply a temporary inflammation of the esophagus or stomach lining.
Oh, okay.
So aside from that, there are absolutely no major serious side effects. There are no severe adverse events linked to using acetic acid this way.
So there is no long-term damage.
Right.
No burning through the stomach lining, no permanent scarring from the acid.
None.
Just some mild temporary inflammation that you would probably get anyway if you ate a particularly acidic or spicy meal.
Exactly. The concentration of the acetic acid used in that 20 cc syringe is carefully calibrated.
Ah, that makes sense.
It is strong enough to trigger the temporary protein shift on the surface of the cells, but weak enough that the biological footprint on the patient is incredibly light. The healthy tissue recovers its normal state shortly after the procedure.
So what does this all mean for you, the listener?
It's a game changer.
It really is. It means one of the most effective, cutting-edge ways to map out dangerous, invisible, precancerous cells across your entire gastrointestinal tract involves nothing more than a highly targeted splash of vinegar and practically zero risk.
It is a powerful reminder of where true medical value often lies.
How so?
Well, we have a bias toward the complex in modern medicine. We often assume that medical progress must look like a newly invented, highly synthesized chemical or, a machine with a microchip.
Right, something shiny and expensive.
But this technique proves that innovation isn't always about inventing something entirely new from scratch.
Yeah.
Sometimes profound innovation is simply about observing how an everyday existing chemical interacts with human biology in a way we never fully leveraged before.
The elegance of simplicity.
Perfectly said.
We took a journey today from a basic 20 cc syringe filled with household vinegar to the brilliant, high-contrast mechanics of acetowhitening.
We sure did.
We learned how the temporary clumping of proteins causes healthy tissue to put on a white disguise, and how dangerous, chaotic cells lose that color rapidly, acting as a secret fading map.
A race against time.
Right. We saw how this simple mist guides doctors to hidden dangers in the esophagus, outlines completely camouflaged flat polyps in the colon, and acts as a real-time chemical blacklight to guarantee every last trace of precancerous tissue is scrubbed from a surgical scar.
And all of it achieved with virtually no serious side effects to the patient.
It fundamentally changes the paradigm for gastroenterologists, upgrading them from relying on blind random biopsies to navigating with absolute visual certainty.
It really is incredible.
It really does. And it leaves me with a thought that is kind of hard to shake.
Oh, what's that?
We have just explored how a common liquid sitting in your kitchen pantry right now has the power to outsmart some of the most elusive, invisible cellular dangers in the human body.
Yeah.
So if a simple splash of vinegar can temporarily pull back the curtain on hidden precancerous cells just by slightly altering how surface proteins reflect light, what other everyday, perfectly ordinary substances might hold the power to expose the hidden biological mysteries inside us if we only knew exactly where and how to apply them?